Right, good morning everyone. My name's Guy Davidson. There's the clue. I work for the Creative Assembly, them. We make games. We make lots of games actually. We have made lots of games. We're Britain's oldest games company. We were formed in 1987. I joined in 1999 and I've been there for about half my working life, which is quite a shocking thought. We make Total War. Anyone heard of Total War? Oh, I love you. Thank you. Thank you so much. We also make Alien Isolation. Anyone play that? Ooh, good, good. Did it scare you? Yeah, all right, good, yes. Job done. Excellent. That was the idea. We made Halo Wars 2. That came out recently. Anyone play that? Anyway, I want to talk to you about what's in store for the C++ Graphics API. This is a paper that's been brewing for a very long time now. The lion's share of it was done by Mike McLaughlin. I joined the effort earlier on this year, but Mike McLaughlin is he's been the driving force behind this, and it would be inappropriate for me to go any further without name checking him. Well done, Mike. Right, this clicker is a bit weird, isn't it? Hang on. Let's try again. Worked this morning. Right, do you know what? I'll use the mouse. Okay, here's the overview. We'll start with a lightning tour of computer displays, because that's really what graphics and display is all about. Then we'll take a quick overview of the API. Then we'll come up with some sample code. And then there's a to-do list, which you can help with. So it's not very picture heavy, this presentation. I've loaded all the pictures at the front, so enjoy them. After this, quite a lot of text. But we'll start with computer displays. Anyone know what this is? All right, before we ask, who was using computers in the 2000s, between 2000 and 2010? Hands if you were using computers then. Good. What about in the 90s? Good. 80s? 70s? You were 70s? No, 80s. 80s. Okay. In your previous life. 80s. And Matesh? No. But you were in the you used them in the 80s? Yes. And what? So what were you using in the 80s? I started with Commodore 16. Commodore 16. Okay. But that was presumably on a cathode ray tube, on a domestic television. Yeah. Yeah, connected to a telly. And you had one television in the house. Yeah, and you fought with your parents about, I want to use the television now. I want to plug my computer in. Yeah, it was fun times. I was the same as well. This is rather older than the 1980s. This is, in fact, the UNIVAC 1 console. It dates from 1951. The display is really, these lights here, which are, it's an irregular matrix. This part of the display here is for displaying characters. So if you want to display an A, display that and that. Also display signal and A. Then you display those two. These levers here are your controllers. So it is a display. The controllers and the view are all mixed up together, so that's very bad. But 1951, baby steps is where we're starting. This is the, anyone? Ferranti Mark I, 1952. Now these are cathodic tubes here, and they each contained a 64-dot display. No, sorry, not 64 dots, 64 lines of 64 dots. And that was actually enough to display the graphics to play a game of checkers. And this is where the first video game probably existed, with somebody playing checkers on a Ferranti Mark I. What about this? Anyone know what this is? It's not an oscilloscope. Good guess. This is the Digital Equipment Corporation PDP-1. What's significant about it, apart from the circular display, which is very futuristic, is Space War. And it was on this machine that Space War was developed in the 1960s. It's hard to find good images of Space War. You've got a bit of a swirl there. And another bit of a swirl there. I'm sure there must be some pictures of it somewhere, but so I've yet to find them. If anybody finds any good pictures of Space War, do Do tweet me with them. The PDP and Space War are quite significant. I mean, not to me just as a games developer, but to me as a programmer, because it heralded an era where programmers learnt their code by writing simple games and puzzles and little things on screens where you get immediate feedback. Computer time started to become a little bit cheaper when the PDP turned up, and people could learn their craft by writing things that didn't matter. It was a waste of time writing these things. You weren't solving important problems, you were just writing games, but you were learning particular aspects of your craft, and that's significant. That's how I learned to program. I wrote games in the sort of late 70s and early 80s. Anyone know what this is? So there are two clues, obviously, UNIVAC and Uniscope. Can anybody be more precise? Or has archaeology been lost entirely upon us all? This is the UNIVAC Uniscope 300. Now, what's significant about this is, well, actually, the aspect ratio. This is from 1964, but you look at the aspect ratio of this screen. This is a cathode ray tube. This is like a TV screen, but it's nice and wide. We're actually looking at the, it's the account of Mr. Benson. So we have dates here. We have the types of transactions. You can see the arithmetic going on here. He was stung for taxes. There $18,000 in taxes, which in 1964 probably hurt quite a lot. But the screen was in fact a matrix of alphanumeric characters. It was known as the glass teletype, and it's here we start to enter familiar territory, because if you're a C++ programmer, you'll know about the teletype, you'll know about TTY, you'll know about character output. Okay, 1964, character output. Okay, bear that in mind. Has anyone used a teletype terminal on VT100 or anything like that? No, I'm really old, aren't I? Do you know what? Warhammer 2 comes out Thursday week. Please go and buy it. But it actually comes out on my birthday, on my 50th birthday. And as I'm getting to 50, as I'm starting to enter this decade, I'm seeing more and more of my colleagues are looking at me aghast when I talk about cathode ray tubes. I used to sit in front of a cathode ray tube and get a big, cathode ray tube tan. Everyone finds this astonishing. All right. Pong. Anyone played Pong? This was 1972. You've played emulations of Pong. You've done the bat ball thing. Great. Finally, I found you. Hello. Hi. My name's Carl. Right. So this hit the US territories in 1972, and it brought games to coin-operated arcades. Now, this is an off-the-shelf cathode ray tube displaying very simple vector graphics. Okay. That little dot there is just the beam going around. You've got a scan there, sort of turning on at intervals for the fence. You've got numbers which are just, it's all straight line vector stuff. Very easy to do. I was about 6 when I first saw a Pong machine, and it changed my life. It made a very distinct impression upon me. I can remember where I was. I actually looked up the hotel where I saw it for this presentation, and it's still there. Not the Pong machine, the hotel. I imagine the Pong machine is in a skip somewhere. I was a big science fiction fan at the time. I was devoted to Doctor Who. I thought, yep, this is really exciting, brilliant stuff. And this was the very thing. So this is probably what got me into developing games and making software. This is a render from the Evans and Sutherland frame buffer. So in 1974, we could suddenly get 640 by 480 pixels, actually individually addressable pixels. So not vector stuff, but actually, right, this pixel has this color, this pixel has this color. Of course, it was still displayed on cathode ray tubes, so it was, not especially precise, but at 640 by 480, good enough. It cost $15,000. You might think your graphics card's expensive now, but 640 by 480, $15,000. But pixel maps are now a thing. Bitmap images, maps of pixels. Any guesses? This is the Apple computer. This is one of the first batch of 200 that was assembled by Steve Jobs, Steve Wozniak, and Ron Wayne. It turns out that the original owner to this one died, and his wife just cleared his stuff out, put it in a skip. It was taken away to recycling. The recycling people found it and said, hang on a minute. One of them spotted it was one of the original Apples, sold it $200,000, gave half to the widow because that was their policy. So happy ending there. But the innovation with this piece of hardware was actually creating a composite video output so that you could just attach it to a domestic television, because at that time the displays were actually really quite an expensive part of the computer. If you could attach your computer to something that everybody already had in the home, it made the computer much cheaper, much more accessible. So home computers, really started to become a thing. Also, by this time, the frame buffer had dropped in price considerably from $15,000 just through mass process, and RAM was getting cheaper. Anyone? This is the Atari 400. Okay. Atari 400. Okay. 1979. This was known as Candy. And it was named after a pretty secretary at Atari. Times were different then. There was also the Atari 800. That was known as Colleen, named after a pretty secretary at Atari. But this was truly a consumer computer for the general public. It made use of the domestic TV, played games, things to plug in, controllers. We're starting to get a flavour of what's going on. I'm just going to move on to early graphics cards. Yes. Now we're talking. Anyone know what this graphics card is? CGA, thank you very much. The Computer Graphics Array. So this came with 16K of video memory. So you had a number of resolutions. You could get 640 by 200 in monochrome. You could get 320 by 200 using 2-bit color. So that gave you 4 colors. That's what this is. Or you could get 160 by 100 pixels using 16 colors, or 80 by 25 text characters using a 4-bit color text mode. Things improved in 1984 with the extended graphics array, 64K of video RAM. You could add another 64K for better color resolution at higher resolutions. You could add a further 128K, giving a truly impressive 256K of video RAM for multiple pages of graphics. So you got back buffering. 1984, suddenly double buffering is a thing. 1987, VGA. And you can't, the difference is not as stark as it was between CGA and EGA, but it's there. You've got 256K of video RAM as standard, 640 by 480 by 16 colors, or 320 by 240 by 256 colors. And then this was followed by all other sorts of GA. I listed them here for fun. XGA, WXGA, FWXGA, XGA+, WXGA+, WSXGA, SXGA, SXGA+, WSXGA+, UXGA, WUXGA. WUXGA actually supported 1920 by 1200, but none of these supported 1920 by 1080. I have no idea where that came from, but you get the idea there. More memory, more pixels, more color. Okay, and there are plenty of cards from the 80s, but you get the idea. It was just more color, more pixels, more resolution, more. Jumping ahead now, LCD displays were a leap forward from the cathode ray tube. This is the ViewSonic VP140. 1997 was when LCD displays started to turn up, and this is actually quite a lovely bit of kit. I had one of these, but the contrast between this and the cathode ray tube was dramatic. And finally, we're now well into the digital age. We've got DVI, HDMI, and they're all transmitting pixel information at a terrific rate across nice fat cables. But before I tell you about the API, I should answer some common objections to this whole endeavor. No one will ever use it. That's nonsense, I think. I've already had encouragement from educational institutions. We've got the history of teaching programming, as I said, involved writing simple games. This is how you learn to write stuff. You put things on the screen, you put up pictures and drawings and charts and graphs and all sorts of things like that. That's how you learn your craft. If only educational establishments use it, that's a win. But they won't be, because, well, there are plenty of libraries already. Plenty of people are actually writing software that requires graphics. Now, saying that there are plenty of libraries already is true, but there are many restrictions to these sorts of things. Licensing restrictions, okay? Only a few years ago did we start using open source software, which immediately ruled out a whole pile of libraries available to us. You say, well, DirectX is there, which is fine if you're writing for Windows. There are all sorts of intersections. There's no universal library that's accessible to everyone to solve all this. It will never be sufficiently performant. This kind of harks back to the customization points thing. What you need to do is focus your optimization efforts appropriately. You know, if you need maximum platform-specific horsepower, then no, I imagine the standard would not be appropriate for you. It's just a toy. This stung a little, but it's not just a toy. It does actually work. This is really a variation of the first and third point. It's entirely functional, what we have so far. It's suitable for a variety of applications. We'll be taking a look at one or two shortly. If you want to read the proposal document, and it is actually quite readable, but it is nearly 150 pages long. This is a big piece of work. So, and we're also still making decisions. So this is very much a bird's eye view. Yeah. You're quite right. Sorry, I didn't catch your name. You have read it, excellent. So the gentleman was commenting that the meat of it is probably 10 pages. You can get the heft of it quite easily. So I would recommend reading it. There'll be a link at the end. But this really is a bird's eye view of what's happening. I'm an English mathematician, in case you couldn't tell. And this is how I spell colour. Yeah, you're from Oregon, aren't you? Yep.
That's how the Canadians spell color.
Yeah, but it's not how the ISO C++... This is not how the ISO C++ standard spells colour. That's how they spell colour. I was pretty grumpy about this, but... Anyway, so our first class is RGBA color. No, all right, our first class is RGBA color. And it consists of 4 pieces of data. Any guesses what 4 pieces of data it consists of? That's tough. Red, green, blue, and alpha. I'm glad you asked that. How many bits? We'll get to that shortly. So values are a floating point, although you can set and read them with integral values too, between 0 and 255. And there's also a set of standard colors, which conform to the CSS colors. Naturally, we need some linear algebra support. So we've got a point, we've got a matrix, and they're all implemented using single precision floating point coefficients. So we'll be introducing linear algebra into the standard, which I think is long overdue.
By the way, matrices are like multiplicable and things like that?
Yep.
Okay. Matrices are like probably standard graphics, like 3 by 3 and so on.
There are, again, dive in, really. Take a look at the paper. There's been quite some transformation since you said you read it in February.
Like 9 months or a year ago.
Yeah, we're up to revision 6 now. I think you'd have reading revision 3 back then.
Maybe, I mean,
Anyway, do take a look. We've got a little bit of geometry, just a little. We have rectangles called bounding box. Not quite sure why we called it bounding box. And circles, which is obviously a position and a radius. And of course we have text. Actually we don't. Text is hard. Text is very hard indeed, but there'll be more on this later. Okay?
and does it support like Arabic and stuff that renders like very differently?
We'll get to this. Okay? Thank you for your interest. Thank you for your questions. I will leave time at the end for as many questions as we can slot in. Right, things start to get interesting now. So remember this point in the description. I'll be referring back to all these things. We need to be able to draw paths. We need to be able to draw lines and curves. Okay, so we have a class called Path Builder that acts as an instruction buffer, and what we call figure items to a path builder. We add these to a path builder to draw things. So these figure items, there are administrative types like new figure, closed figure, translation matrix, and all that sort of thing, as well as the actual line and arc and quadratic curve and cubic curve. These are Bezier curves, obviously. The interpreted path contains the data that results from actually interpreting a sequence of figure item objects. So a typical use case for a 2D API, I say typical, a bit of a stretch case, would be rendering a PDF document. Okay? PDF is an ISO standard library since July 2008, so it's a well-defined target. That's something that we aim to be able to do with the APIs, be able to enable the creation of a standard open source PDF renderer that will just compile everywhere. Naturally, we have brushes. I didn't ask at the start, are we all familiar with 2D graphics? Have we got at least some interest? We've done some drawing to screen, things like that. Okay. If you're finding some of the terms impossible to grasp, do speak up. We've got a wrap mode, and that dictates what happens when you try and sample outside of the brush. You're going to wrap around, you're going to stretch, you're going to just do nothing. We have filters to tell you how to deal with sampling from a pixel map. So this is things like, do you want to use the nearest color or bilinear filtering between 2 points, and that sort of thing. And there are 4 brush types. There's the solid color, which is obviously very easy to filter because it's just the color. And then we have linear and radial gradients. So, you know, kind of like sun ray stuff and horizon gradient stuff. And we actually have a pixel map surface, which is the obvious, the one that's most people are interested when it comes into drawing things. We also have a gradient stop, and this is a point at which a color gradient changes from one color to the next. So gradients are actually formed from a collection of gradient stop objects. The brush class itself is an opaque wrapper for graphics data, and the data is immutable. And it's usable with any surface or surface-derived object, which of course brings us on to surfaces. Now this is the monster, of course. This is the big kahuna. First of all, we have a series of enum classes that describe options for properties of the surface. So we have the enum class anti-alias. So the options there are none, fast, good, or best, depending on how much horsepower you want to throw at the problem of anti-aliasing. We have the fill. We're running short on time. I'm going to race through this. We have the fill rule. We have line cap and line join, what happens at the end of lines and what happens when they join up. We have compositing operations. Then mathematical formula for dealing with overlap when things get together. We've got the format. So this is the pixel format that you were asking about. By default, we define ARGB32, RGB24, RGB16, 565, and RGB30. We're open to suggestions for more formats. Then we have scaling. What happens when the size of the back buffer is different from the size of the display buffer? Do you want to letterbox it or stretch it or fill it or that sort of thing? We have the refresh rate, which was going to be, do you refresh as needed or as fast as possible or at a fixed rate? And we've got the image file format. And at the moment we're supporting PNG, JPEG, and TIFF, all of which are standard formats. Then we have some property classes that collect all these together. The render properties, that covers anti-aliasing and compositing. We have brush properties that cover the filter and the wrap mode and the fill rule. We have the clip properties, which describe the area to be rendered and offers a fill rule. We have stroke properties, which covers line style, so that'll be the width and the cap and the join. And we've got mask properties, which describes the area to not be rendered, if you want to keep something clear. So we can move on to the actual surface classes. So surface is the base class, which offers the common paint operations, so the common drawing operations, paint, stroke, fill, mask. Image surface derives from surface and it provides an interface to a pixel map. Okay. Mapped surface is the next one, which provides access to inspect and modify the pixel data of an image surface. Okay. So this is all that's quite small stuff. But this class, these classes, the next two classes are still in a state of flux, but they're the meat of the paper, to be frank. The display surface class is the abstraction of a window. Okay. Important API in this class includes, the draw callback and other functions such as, changing and reporting the height and the width and resizing the window. And then there's the handler class, and this is the entity which brokers communication between the display window and the operating system. It handles the message queue at the beginning and ending of the display surface lifespan, We'll look into this in more detail in a demo in a moment. Finally, inputs. Like text, this is hard, although it's a little easier than text. Coming soon. So let's look at a few examples. 4 are quite simple. The last is a little more complicated. The first 4 will start with this block of code and assume it's in a main function, okay? So that it fits onto the screen. So we make an image surface. So we're using ARGB32. It's about this wide and this dimension. Then we create a brush, RGBA color black. That means it's black. A foreground brush, RGBA color white. You know what color that is. And then we have some render properties. We're going to turn anti-aliasing off just so that it works nice and quickly. We create a path builder object, and then we paint the back of the window. We do our sample code, and then we save it out to example.png with the file format PNG. And that's what we'll be displaying after I show you each piece of sample code. So, the first 5 instructions of this first sample work on the path builder object. So we create a new figure, draw a line. So the new figure starts at 8020. The line goes 200, moves to 220, 20. So that's going along 200 pixels. Now rel line means draw a relative line, a line relative to where the last one finished. So here we're going along 60 and down 160. The origin's top left, by the way. Then we go back 260. And then we close the figure. Stroke that path onto the image surface. There are 6 parameters for stroking. And voila. Hello, trapezium. Simple? Yeah? Okay. Nope. Nope. You don't need to. We'll come on to that. Sorry. We'll come on to that. I know exactly the point you're making and the objections you're raising. We have addressed those. It's okay. Don't worry. Right, let's try something else. So we're going to draw 2 things now. Here's the first. We've got a new figure. Relative line, 100 along, 160 down, 100 back, 160 up. Okay. Here's the second. New figure, 100 along, 160 down, 100 back, and then close the figure. Stroke it. We're good. Right. Who's expecting to see 2 identical rectangles? Ooh. Who isn't expecting 2 identical rectangles? Who's scared and wants to go back to the teletype? Right. Bang on, Mateusz. They're not quite identical. There was a closed figure for this second one. There wasn't a closed figure here. So what happened is, although these 2 points are the same, that point there, it's quite a fat line. So it doesn't treat it as a closed figure. It simply says, look, we've got 2 line ends here. Here's one line end, and here's another line end. Here we close the figure, which means that rather than having a line end, we have a line join. So we have rules that specify line ends, and we have rules that specify line joins. This line join rule is called miter. Mitering is when you basically join two things with that, and it's effectively a diagonal line that joins the 2. All right, let's try some curves. First, a quadratic curve with a control point. Move to a new position, then another quadratic curve. Don't forget the control point. But this time, we close that figure. Okay? Come on. Right. Now we move a new figure and we draw a cubic curve, which of course will have 2 control points. Then another figure, cubic curve, 2 control points. Then we close it, and then we stroke it with 6 parameters. Is my mouse broken? Right. So there we have a quadratic curve, a parabola, and that's a closed one. Cubic curve, closed cubic curve. Okay? Easy. Right, let's try something a little more exotic. So first we're going to create a scaling matrix. So this shrinks in the x-axis, stretches in the y-axis. So we create a starting point for our shape, taking into account this scaling factor. Apply the matrix to the path builder and start a new figure. We draw an arc. Okay, so an arc is a portion of a circle. So we're going to draw 3/4 of the circle, starting at a quarter pi. Sorry? It's 2017, come on. And then we'll stroke it. Then, right. Time is short. We draw that, then we draw that. The interesting thing is, we've closed our figure, then we draw it, and then we put a translation at the front of our path builder to duplicate the object, and then we fill it. Hello C++. So we do have text. And that's why I stretched it in the x and y axis, so that we'd get a C rather than a Pac-Man. So hello C++, and there'll be kudos to the first person who can submit a hello world pixel map image. Picture of the Earth on black. It's the GitHub repository, which I'll point you all to later. Our final sample is yet more exotic. It's a simple game. It's a version of the Asteroids game, released by Atari in 1980, one of my favorites. And it's a good example because it's simple and it shows off many features. Unfortunately, I left my computer plugged in last night, and it did an update. And now I can no longer run the game, which is extraordinarily disappointing, but I hope will encourage you to go to the GitHub and actually run the game and take a look at it and go, wow, Asteroids, this is brilliant. Right, let's start with the renderer. So the idea is that a default renderer and a default handler will be supplied. They'll be defined in the standard. And it will therefore be supplied as part of the vendor implementation. Okay, and the first renderer that we've written uses Cairo. Okay, it's portable, it's simple, but you can write your own. The interface is well defined, and we'll get onto how you write your own shortly. The first handler we've written is also trivial. That's a dreadful name for a header file, isn't it? Yes, I must have been half asleep or drinking. So for this game, I'm simply using the both, yes. One as a result of the other. Because we do it in our spare time, in our evenings, after we've been, eating and drinking with our families and reminding them that we're still alive. So we're going to use the Stud Experimental IO2D renderer. So this is where all of this lives at the moment. So my renderer is the Cairo renderer. My handler is the Windows handler over my renderer. My display surface on my renderer. And my brush is the brush on my renderer. Close that namespace. So, of course, we need some maths. So we have a class as standard to represent Cartesian coordinates, but the nature of the game requires polar coordinates. So I've added a polar class. We might put one in. Obviously, with all of this stuff, we're building up a linear algebra and geometry use cases straight away. And at the moment, I'm putting them in the sample code. There may be obvious demands to put that in the standard. But if we start adding linear algebra and geometry and things like that, it becomes a much larger can of worms. We'll also require conversions between the two, polar to quasi, pole to car, and car to pole. Awkwardly, they're both pairs of floats, so I wonder if we need an angle type rather than a float type for rotations. Who's heard of tau? It is indeed 2 pi. Has anyone been taught tau is 2 pi? 1 or 2, 3? Yeah, okay. This is an emerging thing. I'm seeing this more and more, that people are using tau instead of 2 pi, which I wholeheartedly support. As a mathematician, I think 2 pi is stupid. We always use 2 pi. We very rarely use pi. You might use pi times diameter to get the circumference of a circle, but actually that's tau times radius, which is much more meaningful. The radius is what defines a circle, not the diameter, conceptually. When you do your differentiation and integration, the numbers become easier when you're using tau instead of 2 pi. Anyway, tau equals, rant over, sorry, tau equals 2 pi. It means 1 turn. Maybe I should have called this geometry. Anyway, then we have to manage collision detection, and we do this with the intersects function, and contains. So if a boundary contains an object, then there's been a collision. In addition, we need to worry about things like the radius of objects. You know, if it's outside the radius of the object, it hasn't collided. We want to be able to rotate them, and we want to be able to move them about. Got to worry about the physics. What we're doing is we're building a model of the universe with asteroids. Have we all played asteroids? Sorry, I'm an old bloke. Asteroid, yeah, thing in space, spins round and round, shoots out bullets. Pff, right. But we're building a model of the universe. We're drawing it every so often. Okay? So how do we model the asteroids and the ship? Oh, with a path buffer. You know, it's just an outline. The asteroid and the ship's just an outline. So it's easy to turn a path buffer into a set of draw instructions too. We also need a collision structure, which tells us all we need to know about, you know, all we need to worry about for whether or not something is colliding with something else. And this needs to be a little bit different for rotating objects, because if something's not rotating, you can make some shortcuts. You always know what the path buffer is to something if it's not rotating, but for the ship, which looks like this, the path buffer changes when it rotates. So we have rotating collision. So our regular objects that we're modeling have an update function, which updates their position according to their velocity. Some objects need to deal, well, actually asteroids need to deal with being divided. You know, you divide them, and then what's the new physics model? You've got something going slowly at this, and then it's split into two, and then it goes quickly in two different directions. So you've got two vectors coming from a single vector. To draw things, we need to know their position, and we also expose the velocity. So why might we do that, since the update function is a member function? Okay, when the ship is destroyed, we want to know where everything's going to be. You know, you don't just like put the ship in and then suddenly have it hit. So we need to be able to build a predictive model of where all the asteroids are going to be. And then, of course, there are objects that can be controlled. They respond to thrust, which changes their acceleration, and they can be spun, which changes their orientation. Now, if we start looking at individual objects with the asteroid, now there's a lot of repetition here. We want to update it, destroy it, draw it, and expose its collision data. The ship is similar. We want to update it, draw it, and destroy it. And the missiles, we want to update, draw, and destroy them. And we also want their collision data. We don't need the ship collision data because everything collides with the ship. So we start all our instructions from there, which is handy because that's the rotating thing, and things become simpler. So we have asteroids, ships, missiles, and physics to model them. So we make the game. Look, an update function, a draw function, and a generate level function. We don't need to destroy the game. The game is the thing that contains all the things that need to be destroyed. Right, it's 20 to 10. Let's consider input. What do we need? We need to get the key states and the individual instructions. Anti-clockwise. Oh, and hyperspace as well. That was in the original game. And finally, we need to worry about our host OS, which is Windows. So we just need to get our key definitions. We need something to get the key states, and we need an entry point. Right, I've said here, let's look at some source. I'm not going to do that because we've got 4 minutes left, and I want to talk about customization points. So the handler and the renderer are already visible as customization points, and the linear algebra is probably going to become a pair of class templates so that you can template them over integral values for display screens, which are in integer pixels, and float values for worlds, for everything else. The current paper doesn't include the linear algebra customizations, but it does include the handler and renderer customizations. So the handler is actually a facade class, which contains some functions for handling the dimensions of the display, as well as the refresh rate and some simple observer modifier functions. But the significant functions begin show and its counterpart end show. That's quite small and easy. The handler, it starts up a message loop and then talks to the display surface. Things become a little more complicated when you come to the renderer. We need to specialize 6 things for the renderer. Remember when I said here's where it gets interesting? Those are all the things that need specializing. Okay? I will show you some code. I've got 3 minutes. Right, where are we? If we look at X surfaces, right. So the image surface is templated over class T, which is our renderer. The display surface is templated over class T. That's our renderer. If we go to the Rocks in Space game, I decided, well, Michael used to be a lawyer, and he said calling it asteroids might be dangerous. So the Rocks in Space game, if we just look at our main function at the bottom, there we are. So we make a display surface using my renderer. We'll make a handler using my handler. And we have a draw callback which passes my display surface in and then calls the update function for the game. If we take a look at the renderer, it's that simple. You can decide, well, I'm going to write my own renderer. I'm going to write my own handler. If we look at xcairo.h, up here, so these are effectively analogs to all the surfaces, the image surface, the display surface, the map surface. These are all implemented separately here. And so the API that's exposed in the standard is simply static polymorphism. It's a facade to whatever's implemented underneath. If you want to write your own NVIDIA GPU renderer, or if you want to write your own Vulkan renderer, or your own DirectX renderer, you can do so. Better still, lobby for your vendors to supply them. Lobby for your vendors to write a DirectX renderer. Write one yourself and sell it to them. I wonder if anyone's already doing that. There's plenty of work to do. There really is plenty of work to do. If we go back here, and we go to slide. Oh, you're kidding me. Don't do this. Oh, man. Talk amongst yourselves. Oh, please. This is all just for one joke that I put in on the final slide. Right, 44, 5, 6, 7, 8, 9. I will finish before 9:46. There we are. To do. Right. Okay. So things that I have to do, or we have to do. Text, as I said. Yeah, it's hard. Actually, what we're going to be doing, the open font format is actually an ISO standard. So we're simply going to say we're going to direct people there. It's 500 pages long, which is why I've said it's hard and it's complicated. It handles everything. Everything that open font format, everything that open font format handles everything. It has rendering Unicode, direction, rotation, the lot. Okay, that should cover everything. Nearly ready. Input, as I said, there is. I'll show you one more piece of code after this, actually. More renderers, as I said, DirectX, Vulkan, OpenGL, Skier. That's got a hardware-backed. Remember, so I will show you a piece of code. That's the next piece of code I'll show you. Okay? We need lots of sample programs, okay? to work this out and also to prove it and demonstrate it and show where the shortcomings are. If you feel like writing that, that would be great. Sound. That's not part of this paper, but it's the thing that's obviously missing when you're playing asteroids. You need the boo, 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 all that sort of sound. I'm a bit busy though, so I'm not going to do that. That's Janet Leigh from Psycho. Total babe. So there we are. Reference implementation there. Go download it. Go pick it up. For best performance, Visual Studio 2017 version 3, the latest bleeding edge. We'll build this all nicely. Any questions? Good question. I'll answer that one now. If we go to, where's the game? Where's the cursor? Ah, there we are. Right. So I've got platform. Right, you can't read that. It says platform files. There is one platform file in here. Okay, and that's it. Okay, this is all that is platform specific in this game. So you have a namespace, an anonymous namespace to keep the keys in, and here are our Windows calls: get key state, and then here's our win main, which is basically run the rocks in space main. Now these will disappear, or these will be folded into the standard when we have the text, when we have the input done. But at the moment, right now, you can download this. You can play a fairly shonky game of asteroids. I haven't got the collision detection working yet for the. There was an older version. It didn't work, but I'm going to work on this next. But this is the only platform-specific code you have for writing a simple 1980s video game, and that'll be gone soon as well. And it's 10 to 10. Sorry, thank you.